take us to stereochemistry. All right. There are basically two rules for stereochemistry. And as long as you know these two rules, you can figure out how all the stereoisomers are made. And here are the rules. First rule is this. Whatever the stereochemistry of the diene and the dienophile are will be conserved. So the stereochemistry and of the diene and dienophile are conserved. Okay, what does that mean? Well, if we take a look at this first example, okay, so in these first two, we're going to be looking at the dienophile, and the other two, we're going to look at the diene. Okay, so our dienophile is this compound right here. Here's the alkene. Is this an E or a Z? Or I'll say cis and trans because disubstituted. Cis or trans alkene? Cis, good. So if they are cis to start with, they will end up cis in the product. So here, this is cis. So that means that in our product, here's our cyclohexene. And here's carbon 1, 2, 3, 4, 5, 6, 2, 3, 1, 4, 5, 6. So if the groups on 5 and 6 were cis on the alkene, they will be cis on the cyclohexene, which means they will both be either on the top face or on the bottom face. I'm going to need to make these a little bit smaller here. So we get a mixture of the two enantiomers. So cis to start with, cis in the product. Cis gives us cis. Okay? That's what it means to conserve stereochemistry. In the next example, on our dienophile, here's the alkene. These groups are trans to each other. If those two groups are trans on the alkene, then they will be trans on the cyclohexene. So here's our cyclohexene. I'm going to go ahead and draw both of them. And one of the ketones will be on the top face and one will be on the bottom face. So you could draw one and say plus the enantiomer, but I will draw both of them out for you. Okay, so we have trans on the alkene, giving us trans in our product. Is that good? All right. So let's now look at the diene. So there is kind of a vocabulary that we use. I'm going to just make this smaller so it doesn't get too mixed up. I'll make it bigger in a second. So there's some vocabulary that we use to describe the groups on the diene. So if you draw your diene in the S-cis conformation, okay, you'll have two groups that look like they're pointing inside of a ring. So if we did a ring right here, can you see how these two groups look like they're inside that ring? Whereas these two groups are outside that ring. We call these two groups the inside groups, these two groups the outside groups. Okay, so the secret is to put this in the S-cis conformation. And if you can imagine a ring here, we have the inside groups and the outside groups. Okay. So this one, it says that the inside groups will end up on the same face and the outside groups will end up on the same face. So outside will get the same face. Same face. And the inside, or the inner groups, will get the same face. All right. So on our diene, in this case, in this reaction here, we have two groups. We have a methyl group and carbon 1 and a methyl group on carbon 4. 1, 2, 3, 4, 5, 6. Okay. They're both outside groups, right? So they have to end up on the same face. So both outside. So let's draw our cyclohexene and put our double bond between 2 and 3. I'm going to put in the rest of my numbers, 1, 4, 5, and 6. Let's add the decoration for 5 and 6 just to get that done. So we have an extra double bond left over and an ester on carbon 6. All right. So we have two methyl groups to put on the diene. One on carbon 1, one on carbon 4. They're both on the outside, which means they're going to end up on the same face. We could have both of them wedged. There's one methyl. There's the other methyl. Plus the enantiomer, where they're both dashed. See, oh, sugar booger. I keep trying to squeeze these in. Lost my group there. CO2Me. Okay. So we get the two enantiomers, but as long as you set one on the top face, the other one goes on the top face. So now let's look at the next example. So on carbon 1 and on carbon 4, they still have two methyl groups. But now one is on the outside and one is on the inside. So how do you think this one's going to go down? What do you think? So let's start. I'm going to put in my numbers. And let's draw our cyclohexenes and our double bond. Our dienophile is the same, so it's going to end up with another double bond and a CO2Me. I'm going to go ahead and draw both of them because we know that we're going to get enantiomers of this. CO2Me. So how is this going to be different than the one we just did? The one we just did had both outside groups. It could have had both inside groups. We don't know because they're going to end up with the groups on the same face. What do you think about these two methyl groups? Opposite faces, good. You can think of that as another way. If you want to, remember that there are hydrogens here, right? Oh. I'm going to make this one pink. Nope, that doesn't stand out very well. Make it green. Okay. So we could say that this outside group on 1 will be on the same face as this hydrogen because those are both outside groups. This green or this inside methyl group will be on the same face as this blue hydrogen because they're both inside. That's another way to look at it. Or you can say one's inside, one's outside. So they're going to be on opposite faces. So one will be wedged and one will be dashed. And then you get the enantiomers. All right, so let's kind of take a second to remind ourselves of what we were doing. So we were working on the Diels Alder reaction. And in the Diels Alder reaction, we have two pieces that come together. We have our diene and we have our dienophile. And that dienophile is a alkene that has an electron withdrawing group on here usually. And we said that electron withdrawing group, we can identify that because it's a carbon that's attached to this alkene, but then that carbon also has a multiple bond to an electronegative atom. So I know we wrote double bond, but let's generalize this and say multiple bond, multiple. Because I don't want you to get confused when you go back through your notes and you look at this one, which is the nitrile, and it's not a double bond, but a triple bond. Okay. So once again, this is where we just added was multiple. And that's just so that you don't get confused when you go back and look at the nitrile. You probably will have done so many examples now that you'll be like, oh, of course, that's electron withdrawing group. Okay. So we said that the electrons that flow in the reaction, there are 3 pairs of electrons. Our first arrow here shows the breaking of one pi bond to make a new sigma bond. So that's 1 pair of electrons. Then that breaks the next pi bond, which those electrons move over to make the new 2,3 pi bond. And the pi bond between 3 and 4 moves over to make the new 4,5 sigma bond. And that's all the arrow pushing mechanism. Everything basically kicks over 1. And that the reaction's favorable because we're breaking 2 pi bonds and we're making 2 sigma bonds. So we're getting rid of weaker bonds and making stronger bonds. Stronger bonds mean it's more stable. So far, so good? Okay. So we also came up with this numbering scheme where if we start at one end of our diene and we number 1, 2, 3, and 4, and then on our dienophile, we number 5 and 6, that would correspond to the product that we got, which is a cyclohexene, where the double bond, the new double bond that's formed is always between carbon 2 and carbon 3. That kind of gives us an orientation. And we apply that to a whole bunch of examples where we did not consider stereochemistry, with the exception of, we said, racemic mixtures. So then we said, okay, let's take a look at the rules for stereochemistry. And there are really just 2 rules. And the first one is nice because it says that whatever the stereochemistry of the diene and the dienophile are, it's going to be conserved. So I'm going to zoom in over here. So we first focus on the dienophile. And we said, well, let's take a look relative to the alkene. If the 2 groups are on the same side or cis, then that means that these 2 groups that are on carbon 5 and 6 on the ring product will also be cis. Okay, so we're just going to keep it how it is. There's no inversion, there's no randomization. Cis would mean cis. And then also with the dienophile, with respect to the double bond here, if the 2 groups are trans to each other, then that means on the ring, the 2 groups will be trans to each other. So far, so good? And you get both of the enantiomers. So with respect to cis, we could have both wedged as well as both dashed. And with trans, you can see we have wedge dash or dash wedge. We get a mixture. That's the racemic mixture that we get. Good? Any questions about that? Okay, so then we focused our attention on the diene. And we said, well, we want to label the diene here. So we looked at the groups that are on either end of the diene. And we have 2 things attached to the end of the diene. We have what we're calling an inner group, and we have what's called an outer group. And that's all relative to this circle that we kind of imagined here, where the inner group is in the circle and the outer groups are outside the circle. Okay. And what we said was this: if we have inner groups, or the inner groups that we have will end up on the same face, and the outer groups that we have will end up on the same face. So we just need to label them. So for example, in our first example here, we have two groups and they're both outside groups, which means that they will be on the same face on the ring. So we drew our first structure of our cyclohexene, and here's the one group, here's the other group. They're on the same face, so we made them both wedged, and we drew the enantiomer where they're both dashed. So far, so good? The next example has an outer methyl group and an inner methyl group, which means that they're going to end up on opposite faces. So we drew our cyclohexene product. We drew in the two methyl groups. One gets wedged, one gets dashed, plus the enantiomer. And then you reminded me that I was way over time, so we stopped there. Good? Any questions about any of that part so far? So far, nope. Okay. So now this is the second rule. And the second rule is called the endo rule. And it really comes from how these two groups come together, which we'll talk about in a second. But this is the rule. It says that the electron withdrawing group and the outside groups will end up on the same face. Okay. So the electron withdrawing groups and the outside groups are going to end up on the same face. So let's put these two pieces together. So here is our first example. We have a diene and our dienophile. We have our two substituents on our diene. And are they inside or outside groups? Outside groups. They're both outside groups. I'm going to put little O's here. And the nitrile is our electron withdrawing group, right? So all of these things will end up on the same side. All right, so here we go. I'm going to draw my cyclohexene. I'm going to go ahead and number 1, 2, 3, 4, 5, 6. We start by putting 2 and 3 on either side of the double bond. And then we can finish numbering 1, 4, 5, 6. Okay. We have our outside methyl groups. Let's pick what face they're going to be on. Let's just pick a face. We're going to say we're going to wedge them. So we have one methyl group that's going to be wedged. The other group is also outside, so it also gets wedged. And the nitrile has to also be wedged because it has to be on the same face as the electron withdrawing groups, as the outside group, sorry. CN. Okay. Plus the enantiomer. And the enantiomer is just the mirror image where instead of wedging the groups, we're going to dash them. It still puts the outside group on the same face as the other outside group and the nitrile on the same face.
Would this still apply when the electron withdrawing group is attached to an alkyne?
Actually, that's a great question. So you may have noticed that I kind of rigged things up here. So when we were looking at the inside and outside groups before, I used alkynes because this is no stereocenter, because it's still sp2 and flat. So if this is an alkyne, this does not have stereochemistry.
Got it. Okay,
Yep.
That makes sense.
If you wonder why I used alkynes for all those examples, that's why. All right, so let's do let's do the next one. Actually, let's add a little something to this. Let's add a methyl group on the dienophile, and let's have it come this way, because I think you guys can kick it up a notch here. Okay, so if you're not sure what I just added, I added this group right here. All right. So don't panic. Let's do what we know. We're going to draw our cyclohexene. And we're going to number. Going to go back to my starting material. At one end of the diene, we number 1, 2, 3, and 4. So be careful that you don't number the methyl groups on here. We're just numbering the carbons with the pi bonds. 5 and 6. So we have 2 and 3 on our double bond, and then we go 1, 4, 5, and 6. Okay, any questions so far? All right, so now you may need to pause and say, all right, where do I start? And I want to tell you, it does not matter where you start, because once you set the first one, everything else is relative. So it's kind of like your choice, and then everything else is relative. So let's start by looking at our dienophile. Our dienophile has my electron withdrawing group, and it has a methyl group. Are those cis or trans to each other? They're trans. So that means that these two groups have to also be trans to each other in the product. Okay. On my diene, I have two methyl groups. Are they inside groups or outside groups? Inside groups. So I'm going to put little I's here so I have everything labeled. All right. So does it matter? Allison, point up or down? Just pick one. You're pointing down. Okay. So the methyl group on carbon 1, we are putting down. Okay. On carbon 4, we have another methyl group. It is also an inside group. So since we put the inside group on carbon 1 pointing down, we have to also put this one pointing down. Got it? Everything's relative to whatever Allison set the first one to be. All right, so now let's look at everything else. Carbon 6 is my electron withdrawing group. Does it get wedged or dashed? It gets wedged. It has to be on the same face as the outside group. Well, the outside group here is a hydrogen. That's my outside group, right? And that's what's wedged on carbon 1. So that means that the nitrile has to be wedged. Questions about that part? Okay. If it's on the same face as the outside groups, that means it's on the opposite face as the inside groups. Okay. All right. We have one more piece to put on. We have the methyl group on 5. If this is trans in our dienophile, it must be trans in our product. If CN is wedged, then that means the methyl group must be dashed. And that's the strength of this reaction. This gives us 4 different stereocenters in one reaction. So we get this plus the enantiomer. And in our enantiomer, we're just going to switch what's wedged to dashed and what's dashed to wedged. So this is the one we would draw if Allison had pointed up first. Okay. So I don't want you to panic about where do I start? Where do I put the first one? Okay. That's what happens a lot. People are like, I don't know where to start. Just pick one group, put that one group on a wedge or a dash, and then everything is relative to that based off of these rules. All right. So what I actually want to do here is, let me add a page. We can make them as like a little model. Okay. So let's attempt to do this. Here is a stereochemical model. So here is our giant cyclohexene. And actually, before I do that, let me move that over. Let's draw the diene and the dienophile. So here is my electron withdrawing group. By the way, I just want to point out, I draw the electron withdrawing group this way, but it's the same as if I had drawn it this way. So if you see it flipped over, it's the exact same thing. I just tend to, this looks awkward to me when I write it, which is why I tend to write it this way. Okay, so let's put our groups on here. We have inside groups on our diene. We have outside groups on our diene. On our dienophile, we have cis and trans groups. Here's my trans group. And here is my cis group. Let's make a model that we can use to summarize all of our rules. Like I said, it does not matter where you start, just start someplace. So let's go ahead and start by putting the outside groups on. Okay. So I'm going to start and I'm going to wedge this outside group. Once I make that decision, everything is relative to it. The other outside group is wedged. The inside groups are dashed. The electron withdrawing group, is that wedged or dashed in this one? Wedged because the outside groups are wedged. So my electron withdrawing group is wedged. Okay. If my electron withdrawing group is wedged, then that means that my cis group is also wedged. And my trans group is dashed. And that summarizes all of those models. It's kind of cool, huh? All right, so that's one. I want to make sure to draw the enantiomer so that you have it. And of course, I moved it over way too far. All right, so we're just going to make everything that was wedged dashed and what was dashed wedged. Here's my outside group. My outside group, they're dashed. Inside groups wedged. My electron withdrawing group now has to be dashed also. Electron withdrawing group. My trans group now is going to be wedged. Trans. And my cis group is dashed. So that might be a helpful kind of summary for you. Good? All right. So there's only one more little piece to the Diels Alder puzzle, and that is in a case where one of the two groups is not symmetrical. So what you may or may not have noticed in all of these examples, let me go up here to problems, is that at least one of all these substituents is symmetric. So if I put a line through here, what's on the top is reflected on the bottom. So see how all of these have at least one reagent that's symmetric? Okay. We need to look at the case where that's not true. And this is going to tell us regioselectivity. So this is much less common, but you're going to see it. So with our unsymmetric or non-symmetric reagents, we are going to need to figure out where groups are relative to each other. And hold on one second. Something just opened on my screen here. Okay. So what we're going to compare is where the electron withdrawing group on the diene file, I miscalled the diene, on the diene file is relative to one of the groups on the diene. That group is usually what we call an electron donating group. Okay. So we have withdrawing on the diene file and we have donating on the diene. Okay. So what are your donating groups? These are ones that can donate electrons. So think about these as ones that will help to stabilize a carbocation. That's these kinds of groups. So we have OR, NR, OH, and even R groups. How do we recognize them? They are either atoms with lone pairs. So atoms with lone pairs, or an alkyl group, which is your R group. Okay. Those are considered donating groups. All right. So when we have to consider regiochemistry, there are two cases. One is where our electron donating group is going to be on the end of the diene, and the other one is when it's on one of the middle carbons. Okay. So we have case 1 and case 2. In case 1, what will happen is that our product, which is our cyclohexene, will put those two groups one carbon away. Electron donating group and electron withdrawing group. Not like this. Oop. EWG. Okay. Where does the second one come up from? That is if I flipped this over and put the electron donating group here. Okay. It's going to bring them together this way. All right. And this happens due to resonance and buildup of charges in different places. So this is due to resonance and partial charges. And partial charges. Okay. And I wasn't planning to go over that now, but I'm happy to go into that in more detail tomorrow if you'd like. The other case is a case where our electron donating group is on the inside. And what will happen then is that they will line up opposite each other. Oops, that's black. That black, this is black. So now our electron donating group will end up opposite of our electron withdrawing group. Not 2 carbons away. Okay. And once again, it has to do with resonance. And I'll give you kind of a quick overview. If we take resonance into account and we have a donating group on, it will push electrons all the way to the end, which will give this a partial negative charge. It pushes electrons all the way through the system. If you have a withdrawing group, it's going to pull electrons from the alkene, and it creates a partial positive charge here. These two line up. Okay. If we have an electron donating group on the inside, it will push electrons to the end right here, which does not line up well if the electron donating group is situated 2 carbons away, but rather if we rotate around this group and put delta plus here. I'm never going to ask you to repeat this, but I wanted to give you at least some insight. So it's all about lining up these partial charges, and that's what gives rise to the different regioisomers. Okay? Good?
Does the stereochemistry from above still apply here as well?
Absolutely. Absolutely. In these pictures, we're just looking at the regiochemistry.
So then in the first one, would they would both be on the same side?
Exactly. Now that electron donating group could have been put this way, which is why I didn't want to draw just one. I'm sorry. So it could be on the inside, in which these would be on opposite faces. But yes, all those rules still apply. This doesn't change any of that.
And then in case 2, that's also an outside group. So
actually, it doesn't have stereochemistry.
Oh yeah, because it's okay.
Exactly. Yep.
Got it.
We're gonna do some examples now. Okay, make sure we have this. So this is just going to be kind of a hodgepodge mixture of everything. Ready? Okay. So this is how I would approach my Diels Alder reactions. I want to know what rules I need to worry about. So first question I would ask is, do I have symmetry in either one of my reagents? Do I have symmetry in this one? Yes. As soon as you say yes, you do not need to worry about regiochemistry. So first question, are either reagent, oh, I forgot my A in there. That's why it looks funky. Reagent, symmetric. If you say yes, you can ignore, or you don't have to take into account regiochemistry. What we just learned about donating and withdrawing groups. So I would ask yourself that right away, because it takes a lot of pressure off. Okay, so on our first one, we said yes. In this 5-membered ring, we can divide that right in half, and that's the top is reflected in the bottom. The dienophile is not, but it doesn't matter because one of the reagents is. Okay, so let's go ahead and draw our product. I'm going to draw them so that trying to think the best way to do this. I will try to do them one on top of the other for the 2 different stereoisomers. So here's my 6-membered ring. I'm going to go ahead and draw both. Okay. And let's do our numbering. 1, 2, 3, 4, 5, 6. So this example is one, remember I was saying it doesn't matter if the electron withdrawing group is shown on the left or the right. This is an example of that. So here's one where I drew it on the left versus this one where I drew it on the right. Okay, so let's put our decoration in, and let's start with carbon 6. So we have 2, 3, 4, 5, 6, 1. Carbon 6 has a methyl ketone. Okay. Carbon 1 has a CH2 group that's also attached to carbon 4. So I'm going to put a little dot here for that carbon, and I'm going to connect carbon 1 and carbon 4. Okay. Now let's do some wedges and dashes. Do our stereochemistry. So is this carbon that we just drew here, is that an inner group or an outer group? It's an inner group, right? Outer groups would be pointing out away. So I'm going to go ahead and just wedge those. I could have dashed them first, but I'm going to wedge them. And you just wedge them like you would any other bond. Just like that. They're inner groups, So what can we say about our electron withdrawing group? If we wedge the inner groups, what does the outer group get? It gets dashed. So we're going to go ahead and dash that one. And our enantiomer. So that means that in the enantiomer, our ketone is going to get wedged. This is a little bit harder to draw. This is why I use the little dot method. I'm going to put my dot here, which is the carbon where they share. And I'm going to dash to 4, and I'm going to dash to 1. Okay? So those are the 2 stereoisomers. Any questions about that? Nope. Okay. All right, let's look to the next one. Do we have either one of these reagents being symmetric?
Yes.
Yes. This one over here is symmetric. Okay. So that means we don't have to worry about regiochemistry. Let's just jump to our product. So we're going to have 2 cyclohexenes for the 2 enantiomers. Okay. And we number 1, 2, 3, 4, 5, 6. All right. So let's take a look at what we have on the diene. On 1, we have a methyl group, outside or inside? Outside, good. On 4, we have methyl group, inside, good. And attached to 6 and 5, it happens to make a ring, but these are cis groups, right? So this is cis. Oh, I made that way too small, sorry. This is cis. Cis. All right. So we're just going to pick one side. All right. So here is, let me number 2, 3, 4, 5, 6, 1. So carbon 1, outside group. Sadie, point up or down?
Up.
Up. So it is going to get a wedge. So what does that tell us about the group on 4? Is it wedged? Nope, it's dashed. 6 has my electron withdrawing group. So does 5, but let's just treat 6. It has to be on the same face as my outside group, so it gets wedged. And there's a ketone. Okay. It's okay, Abby. And my group on 5 is also cis, so that gets wedged. And they're connected through a carbon. How's that? The last bond was really ugly. Let me try to make it a little bit better. All right. Now see if you can draw the enantiomer. I'm going to go ahead and draw it, but see if you can draw it without looking, and then check with what I draw. How'd you do? Yeah. You're liking this one now, aren't you? It's kind of nice and nice way to end. All right. We ready for the next one? Yep. Okay. Are either of our reagents symmetric? No, neither one. If you try to draw a line through the middle here, nope, here, nope. So that means we have to pick which of our cases we're looking at. So here's our electron withdrawing group. And on our diene, our electron donating group is this methyl group. This is our electron donating group. It's on an end carbon. So I'm going to go back up to our models here. Electron donating group on an end carbon is our first case. So that means that our two groups are going to end up next door to each other. So I'm going to go back down. And that means that this carbon is going to end up next to this carbon. So it might be helpful to redraw. What I'm going to do is flip over my diene so that that methyl group is up top. There's my dienophile, because we know that these two carbons now are going to end up next to each other. Everybody see what I did? I just took this one and just kind of flipped it over. All right, so if we number 1, 2, 3, 4, 5, 6, we should be able to get to our products. Okay, so by flipping it over, what we basically did was we changed the numbering, right? It would have been number 4 in this way, but we flipped it over so we had the right regioisomers lined up. So now it actually became carbon 1. All right, so we draw our products. Uh-oh, songs are coming out. That's not a good sign. 2 cyclohexenes. Let's go ahead and number 2, 3, 4, 5, 6, 1. Okay, more people are looking up than down, so I'm going to pick up for my carbon at 1. It is an outside group, so my nitrile will end up on the same face, plus the enantiomer. Good? How you feel about that? So excited. Can I move or no? Still drawing. Still drawing. Okay. All right, let's look at the top one here. I'm on that same page, just up at the top. Are either reagents symmetric? No. So that means we have to worry about regioisomers. Okay, I'm going to look at my diene. And here's my electron donating group. It is on an inside carbon, or carbon number 2. Okay. Here's my electron withdrawing group on my dienophile. Okay. So what I want to know is if I have these lined up in the right configuration, or do I need to flip one? So I'm going to go back and look at the case where the electron donating group is on carbon 2. So that is going to be case 2. So now what we need to do is line these up so that the electron withdrawing group and the electron donating group end up opposite of each other. Okay. So in the example, we flipped over the dienophile, excuse me. So I'm going to do that here. And I'm going to flip this over. Where's the best room to do that? I'm just going to flip it over here. CO2Me and my methyl group. Now I number. Start at the end of my diene. 1, 2, 3, 4, 5, 6. Number it how you have it drawn. Okay. Got it? All right. If you're not 100% sure on that, maybe this will help. Here's our product, and I'm going to go ahead and number. Okay. We want the donating group and the withdrawing group to be opposite of each other. The donating group is on carbon 2, which means that the withdrawing group has to be on our carbon 5 in order for them to be across from each other. Okay. That's why we flipped it over. All right, so now let's just put the groups on. The donating group is a methyl group on carbon 2. Whoop. And there's no stereochemistry there because it's sp2 hybridized. It's just my methyl group. You don't have to write in methyl group. I'm just trying to make it stand out a little bit more. Okay. Carbon 6 has a methyl group. You want that pointing up or down? Okay, I see people pointing up, so I'll make it pointing up. Okay. Once you set the first one, everything else is relative, so we don't stress over that first one. If that group is wedged, the other group is trans to it, so it has to be dashed. Good. So then this group, which is our electron withdrawing group, has to be dashed. Plus the enantiomer. So now the methyl group is down. And the electron withdrawing group, the ester, is wedged. Okay. So I want you to try these last two later on. Okay, don't do it right now. Do it a little bit later on to make sure it's stuck with you. And then I'll post what those look like on Blackboard. Okay, good.
What about the carbons on the attached to carbon 1 and 4?
1 and 4. I'm sorry, which problem are you on? Oh, thank you. I hadn't finished the problem. Oh my goodness. Thank you. Thank you. I didn't put all the decoration on. So what did I not put on? Thank you so much. Is what's attached to carbon 1 and 4. So how do we do that? Well, we are going to do the same thing that we did with this one over here. But now instead of 1 carbon in the middle, there are 2. So I'm going to put 2 dots. Let me erase that extra thing. I'm going to put 1 dot here and 1 dot here. 1 dot here and 1 dot here. Okay. So now, thank you so much, whoever pointed this out. Question, are these inside groups or outside groups? Inside groups. Where are they relative to the electron withdrawing group? Same phase or opposite phase? The outside group has to be on the same phase as the electron withdrawing group. So the inside is to be on the opposite phase. So here's my electron withdrawing group. It doesn't matter that it's at carbon 5 now. These inside groups have to be the opposite, which means they're going to be on wedged bonds. Wedge, wedge, connect. And on the opposite, or on the enantiomer, they're going to be dashed, dashed, and then connect. Thank you very much.